Welcome to part 2 of the tutorial on non-truthful mechanism design. In this part, we're going to talk about a couple applications of revenue equivalence, and in particular, we're going to use revenue equivalence to understand equilibrium in symmetric environments. In the next next section of the tutorial, we're going to give a method for providing robust analyses of welfare in equilibria in asymmetric environments. This section is going to be on revenue equivalence and applications. In particular, we're going to use revenue equivalence to analyze equilibria in symmetric environments and show that these equilibria are efficient. Great. So we just saw the characterization of Bayes-Nash equilibrium that says that interim allocation and payment rules are induced by the Bayes-Nash equilibrium of a mechanism if and only if the allocation rules are monotonically non-decreasing and the payment rules satisfy the payment identity. We called this payment identity revenue equivalence, and we geometrically saw that what's happening was the surplus is being split into a payment, which is the area above the allocation rule, and a utility, which is the area below the allocation rule. And so while we called it revenue equivalence, and typically referring to the fact that the payments given two different auctions that have the same equilibrium allocation rule, we could equally well have called it utility equivalence, because that is also the same for two auctions with the same Bayes-Nash equilibrium allocation. Great. In this section, we're going to describe the method of revenue equivalence, which is use revenue equivalence to observe very quickly properties of equilibria. The method of revenue equivalence equates two equations for payments. The first equation comes from the mechanism rules. Okay, a first price auction. If you win, you pay your bid. That comes from the mechanism rules. The second price auction. If you win, you pay the second highest bid. Okay, the second equation is going to come from revenue equivalence or the payment identity. Okay, your expected payment is going to be equal to the area above your allocation rule. Good. So we're going to see two examples of the method of revenue equivalence. The first example we're going to use to solve for the symmetric Bayes-Nash equilibrium in IID first price auctions. And in the second example, we're going to show that there don't exist asymmetric Bayes-Nash equilibrium in IID first price auctions. Combining these two results together, we see that the Bayes-Nash equilibrium in the first price auction is unique, symmetric, and welfare maximal. Why is it welfare maximal? Well, when we solve for the symmetric Bayes-Nash equilibrium, we observe it to be everyone bids by a symmetric increasing function, and therefore the highest bidder is also the highest valued agent, and therefore the first price auction optimizes welfare. Great. So first, we're going to look at solving for Bayes-Nash equilibrium using the method of revenue equivalence, equating two equations for payments. Great. Our theorem is going to be the following. In the IID first price auction, the symmetric Bayes-Nash equilibrium has the bid function of the agent being equal to the expected second highest value conditioned on the value being the highest value, meaning conditioned on the second highest value being less than the value. Great. To see this proof, first we're going to make a pretty good guess. So if there's a symmetric Bayes-Nash equilibrium with increasing strategies, it must be that the highest valued agent wins. So let's guess the highest valued agent wins. Well, if the highest valued agent wins, then the first price auction is revenue equivalent to the second price auction. Both auctions in equilibrium will allocate the item to the agent with the highest value. Great. Well, then we can start using the mechanism rules to identify what the payments are. So we'll first look at the second price auction and calculate the expected payment made by an agent with value V conditioned on V winning. Well, if you win in the second price auction, you pay the expected second highest value, conditioned on that second highest value being below your value. What is the overall payment in the second price auction? Well, it's this conditional payment on winning times the probability you win, plus your conditional payment on losing, which of course is 0. All right, what about the first price auction? In the first price auction, your expected payment when your value is V, conditioned on winning. Well, it's a first price auction. So by the mechanism rules, if you win, you pay your bid. So it's exactly equal to the bid you give with value V. All right, and then similarly to the second price auction, your total expected payment is equal to your expected payment on winning times the probability that you win, plus your payment on losing. But for the first price auction, that's 0. Okay, so we see that for both these auctions, we calculate the expected payments conditioned on winning. Now, these auctions have the exact same allocation probability, so that the total expected payments is equal to this calculated payment times the same number, the allocation probability. Thus, we can conclude by revenue equivalence that actually these two quantities are the same. The expected payment conditioned on winning is the same in two auctions, which means that the bid strategy in the first price auction has to be equal to the expected second highest value conditioned on your value being the highest value. It remains to check that our guess at the beginning was correct. Okay, so we guessed the highest valued agent wins, and so we need to now check our guess. So indeed, for continuous valuation distributions, this function, the expected second highest value conditioned on V being the highest value, is monotonic in V. Therefore, the highest valued agent wins, and our guess is correct. Okay, so we saw how to use revenue equivalence to solve for the symmetric equilibrium in a first price auction. Next, we're going to use revenue equivalence to prove there are no asymmetric equilibria. For this lecture, I'm going to stick to single item auctions and assume the strategies are continuous. You can see the original sources for relaxing these assumptions. Okay, the theorem I'm going to want to prove is the following. In the IID two-agent first price auction with an unknown random reserve, there are no asymmetric equilibria. What do I mean by an unknown random reserve? Imagine the following scenario. The auctioneer draws a random reserve from a distribution, a known distribution, but the random reserve drawn is unknown. The agents bid knowing this distribution of random reserve, but not knowing the actual reserve drawn, and they bid in equilibrium. And the mechanism selects as a winner the bidder with the highest bid, as long as that bid is above the reserve, and using first price payment rule of the winner pays their bid. Great. I want to use this theorem first to prove the following corollary. And this corollary is probably what you thought I was going to prove in the first place. In the IID n-agent first price auction, there are no asymmetric equilibria. Okay, before we get on to the proof of the theorem, I want to say how to prove this corollary from this theorem. So here's how to prove the corollary. Well, let's consider agent 1 and agent 2. Well, looking at their equilibrium, we can view the bids of the other agents as an unknown random reserve. And then our theorem says that agent 1 and agent 2 must be bidding symmetrically. Great. Well, the same argument can be applied to agent 1 and agent I for any agent I. Thus, all agents must be bidding symmetrically. Thus, we see there are no asymmetric equilibria in the IID n-agent first price auction. All right, now we're going to prove our theorem. Okay, the proof of the theorem is going to be based on revenue equivalence. In fact, as I alluded to before, there's an equivalent theory of utility equivalence, and that's what we're actually going to use. So in fact, we're going to use two equations for utility, one based on the definition of the mechanism, and one based on utility equivalence. Okay, so the first equation for utility is the following. The utility of an agent with value V is equal to their value minus their bid times the probability they win with value v. Okay, this comes directly from the definition of a first price auction. In a first price auction, your utility is your value minus your bid times the probability you win. Great. The second equation for utility is just the equation coming from the payment identity, which is the utility's area underneath the allocation curve. Great, so here's our theorem. We want to show that for two agents, first price auction with an unknown random reserve, there are no asymmetric equilibria. We're going to give a proof by contradiction. Let's assume that the strategies of the agents are not the same. So they're bidding with different bid functions. And let's assume those strategies cross twice, once at a value b prime and again at a value b double prime. So here I've drawn bidder 1 bidding higher than bidder 2 between v prime and v double prime. And I've drawn bidder 2 bidding lower than bidder 1 between v prime and v double prime. Okay, I'm going to assume that the strategies cross twice. There are two other cases, the case of crossing once and the case of not crossing at all. In fact, the analysis you'll do in either of these cases is essentially the same. And so for simplicity, I'm going to just prove this case. Lemma that's going to be useful in this proof is the following. At value v, if bidder 1 is outbidding bidder 2 when bidder 2 has the same value v, then the allocation probability of bidder 1 is greater than the allocation probability of bidder 2. Moreover, if they're bidding equally at some value v, then their allocation probabilities are equal. Okay, so just to dive into this lemma a little bit more, what we're saying is if given agent 1 has some value v, they're outbidding what bidder 2 would bid if they had that value too. Then the interim allocation probability of agent 1 at that value, meaning the probability that agent 1 wins given that value, taking expectation over everything else happening in the auction, is bigger than the allocation probability of bidder 2 when bidder 2 has that value, given everything that's happening in the auction. Okay, this lemma should seem intuitive, bidding more likely to win. We'll prove it formally on the next slide. Cool. So by our lemma and this assumption that bids cross and bidder 1 is outbidding bidder 2 on this interval, we see that the allocation probability of bidder 1 is strictly more than the allocation probability of bidder 2 for values strictly contained in this interval. Great. So by our second equation for utility, we can write the difference in utility that the agent feels between value b double prime and value v prime as the integral of the allocation rule between v prime and v double prime. In other words, if we look at, remember the utility that an agent has at any value is the integral of the area underneath the curve. And so we subtract the integral of the area underneath the curve at the small value with the area underneath the curve at the big value, and the remainder is the area underneath the curve between the two values. Okay, so the difference in utility is this integral from v prime to v double prime of the allocation probability of the agent. Okay, and then by the lemma, this allocation probability for agent 1 is strictly higher than the allocation probability for agent 2, so that that integral is strictly bigger than the integral for player 2's allocation probability, which is equal to, by the payment identity, the difference in utility for agent 2. Okay, so we see applying the second equation for utility and using our lemma that the difference in utility that agent 1 feels on this interval is strictly more than the difference in utility that agent 2 feels on this interval. Okay, but similarly, we can apply the lemma and the first equation for utility at the endpoints. Okay, so what I want to observe is the first equation for the utility and the lemma at the endpoints imply that that both agents have the same utility at the lower endpoint v prime, and both agents have the same utility at the upper endpoint, v double prime. Why is that the case? Well, what does our lemma say at the endpoint? Well, at the endpoints, the bidders are bidding the same. Okay, so they have the same bid, so they have the same allocation probability. Now we can jump back and look at the equation for utility that we have from the definition of the auction rules. And we see that the utility is value minus bid. Well, they have the same bids and they have the same values, times the allocation probability. Well, that's also the same by the lemma. So everything here is the same for both bidders. So we observe that they have the exact same utilities at both endpoints. Well, that's a contradiction, because previously we saw that the difference in utilities at the endpoints was bigger for agent 1 than it is for agent 2, and now we see that the utilities at the endpoints are equal. Well, the difference can't be bigger and have the utilities at the endpoints be equal. So that's a contradiction to our assumption that the utilities cross twice. As I said, the case that they don't cross and the case that they cross once, there's a similar analysis, and so we see that the strategies have to be the same everywhere. Okay, now we're going to prove the lemma. Okay, so the lemma says, again, at any value v, if bidder 1 is outbidding bidder 2 at this value, then bidder 1's allocation probability is strictly higher than bidder 2's allocation probability. So let's look at our picture again. So we have some value v, where bidder 1 is outbidding and bidding b1, which is a high value, bidder 2 who's bidding b2, which is a lower bid. Great. So let's see what's happening given these strategies. And first, let's note that when is bidder 1 beating bidder 2? So bidder 1 is bidding B1. And bidder 1 beats bid 2 as long as bidder 2's bid is less than B1, which happens as long as bidder 2's value is less than B2 inverse of B1, okay? So less than this high value, okay? So bidder 1 beats bidder 2 as long as bidder 2's value is less than this high value. What about bidder 2? Well, bidder 2 beats bidder 1 as long as bidder 1's bidding below bidder 2's bid at this value, okay? But that's relatively a lower value, okay? So bidder 2 beats bidder 1 as long as bidder 2's value is less than this relatively lower value. Great. So now we can write down an equation to what the allocation probabilities are. So remember, there's a random reserve drawn from the distribution. Let's call that random reserve b hat. Great. And so what is the allocation probability of agent 1? Well, agent 1 has to beat out the bid of agent 2, and agent 1 has to beat out the random reserve. Okay, so the random reserve needs to be below B1, that's this value, and the other agent's bid has to be below B1, that's this value, which means their value has to be below B2 inverse of V. Okay, so the probability of each of these things is, well, for the random reserve, it's just given by the CDF of the reserve distribution, and for bidder 2, it's given by the CDF of the value distribution, evaluated at the upper bound on the value at which bidder 1 wins. Okay, we can do the exact same thing for bidder 2. And so bidder 2, their bid has to be below, the random bid has to be below bidder 2's bid, which is this value, and bidder 1's value has to be below the inverse of bidder 2's bid, which is this value. Okay, and so plugging those into the CDFs again, we see that in both cases for player 2, the parameter we push into the CDF is strictly smaller. Okay, and CDFs are, for continuous distributions, are strictly monotone. So the allocation probability for player 2, which is the product of those probabilities, is going to be strictly smaller than the allocation probability for player 1. Great. So this concludes the lemma. Great. I want to briefly describe how this result generalizes from first price auctions to a much bigger family of symmetric winner pays bid auctions. In particular, I want to talk about IID winner pays bid position auctions. Okay, a position auction, there are n positions. Each position is described by an allocation probability where position 1 has allocation probability W1, and the probabilities are in decreasing order down to allocation probability Wn for position n. Okay, the bidders bid in this auction. They're assigned to positions in order of bids, and the bidder in position J is allocated with probability Wj according to the allocation probability of the position. It's a winner pays bid mechanism, so the agents pay their bids if they're allocated. The picture you should have in your mind is the following, where we can take these allocation probabilities for positions and sort them in decreasing order, and we're going to get the bids and assign the highest bidder to position 1 with allocation probability W1, the second highest bidder to position 2 with allocation probability W2, etc. Great. So the theorem is that in the Bayes-Nash equilibrium of the IID winner position auction, it's unique, symmetric, and welfare optimal, meaning one, we can use the same method of revenue equivalence to solve for equilibrium here to solve for the symmetric equilibrium. And two, essentially the same proof of the non-existence of asymmetric equilibria that we were just talking about for the first price auction also applies for IID position auctions. The only thing we have to change from our previous proof is the lemma that we just had on the last slide. And it's a slightly more complicated lemma to argue that if you're outbidding another bidder in the IID position auction, you have to be having a higher allocation probability. Great. So we see, so quite generally, in symmetric winner pays bid auctions, the outcome is unique and symmetric. And because the highest valued bidders are going to be bidding the most, then the highest valued bidders are going to be getting the highest positions. And so the equilibrium is going to be welfare optimal, meaning we're optimally assigning to maximize welfare. Great. So that concludes section 4, 2 applications of revenue equivalence and analysis of equilibria in symmetric environments. Okay, this section is going to be on the robust analysis of equilibria. We're going to give simple, powerful methods for analyzing equilibria and showing that the welfare of equilibria are pretty good in asymmetric environments. Just to point out some of the references here, the Alan Borden and Brennan Lucier's paper about the price of anarchy for greedy auctions, excellent paper that shows that simple greedy procedures can have better equilibria than mechanisms based on optimal algorithms. I also want to call attention to the composable and efficient mechanisms paper by Vasilis Serganis and Avatardos, which identified simple properties of mechanisms for which they had good equilibria, and moreover, compositions, mechanisms that are composed of these simple mechanisms also have good equilibria. Cool. So I want to begin by focusing on a large family of winner pays bid mechanisms. Okay, and this generalizes the first price auction we've been talking about. Okay, so in a winner pays bid mechanism, we're going to solicit bids. We're going to run some allocation algorithm to map the set of bids we have to a set of winners, and then the winners pay their bids. Okay, so the only variable that you have here to change the mechanism is in step 2, and our question here is, well, which algorithms are good algorithms for mapping bids to who wins? There's one sort of focal algorithm that we might consider, and that is the highest bid wins algorithm. That's the one that we were using for the first price auction. Let's allocate to the feasible set of agents that has the highest total bid. Okay, so that's again from previously in the tutorial. That is, we're going to choose the allocation that's in the argmax of the sum over the agents of of bid I times allocation I. Let's look at an example where equilibria might not be great. Okay, so the first example is going to be just selling an ad space, as you might see on maybe CNN's homepage. Okay, imagine I have one ad space, I have two agents, and I want to use a winner pays bid, highest bid wins mechanism for selling this ad space. Okay, imagine the values are 101 and 100, and imagine these approximate Nash equilibrium bids. Okay, so the bidder whose value is 101 bids 100 and a penny, and the bidder whose value is 100 just bids 100. Okay, and these are approximately a Nash equilibrium. The bidder with value 100 can't change to get a higher utility, and the bidder with value 101 could only get at most a penny by optimally deviating, and so this is an approximate Nash equilibrium. Okay, so what's the outcome? Well, the bidder with value 101 wins and pays 100 and a penny. And so the welfare is this bidder's value, so it's 101. And the optimal welfare is going to be also 101. So this is actually, we're doing it as good as we could possibly do. Great. Let's slightly change the scenario let's suppose that we could sell this ad space, but we could either sell it to one advertiser or we could split it up and have it shared amongst three advertisers, which will have three ads that are sort of a third the size. Great. Okay, and then let's imagine we have some agents who have values for this ad space. Imagine we have two agents who want the ad exclusively, and their values are the same as before, 101 and 100. And then imagine we have three agents who are happy to share the space, and their values are 99, 98, and 97. Cool. So here are some approximate equilibrium bids. It's the exact same bids as before for the exclusive agents bidding 100 and a penny and bidding 100, and the other shared agents all bid 0. Okay, I want to point out that this is indeed an approximate Nash equilibrium again. Well, the exclusive agents have the same equilibrium strategies before, and the shared agents, well, none of them can unilaterally deviate to win without having to pay more than 100, and they don't want to because their values are low. Great, so what's the outcome of this equilibrium? Well, the agent with value 101 wins, pays 100 and a penny, the welfare is 101, but now we're leaving a lot on the table. The optimal welfare is almost 300. Cool, so this is an example that shows that winner pays bid mechanisms can potentially, in more complicated scenarios that we've studied so far, have bad equilibria. Okay, so the goal of this part of the tutorial is to give a simple and powerful method for understanding when winner pays bid mechanisms have good equilibria. This method will start with a sort of an overview of the geometry of best response. Okay, and best response, the geometry we're going to be talking about basically has the following intuition. The intuition is, well, an agent's best responding, so either they're going to get high utility or there's a reason they're not getting high utility. The reason they're not getting high utility is because there's lots of competition and they can't compete. Cool, so let's look at our interim bid allocation rule. So this is a bid allocation rule. So we're mapping bids on the x-axis into allocation probabilities. Okay, and a winner pays bid utility, as we saw previously, given a value that the agent might have and a bid that they might place, is value minus bid times the bid allocation rule, the probability that the bidder wins given that bid. Okay, so this utility I can depict geometrically on this figure. Okay, on the x-axis, I have the width of this rectangle equal to v minus b. Okay, that's this term in the utility function. And I have the height of this rectangle equal to x tilde of b, the allocation probability that the bidder has when the bidder bids b. Okay, so this rectangle is the bidder's utility. And with a value v, what does this bidder want to do? They want to find the biggest rectangle they can fit underneath the bid allocation rule. Cool. I want to view this bid allocation rule, x tilde, as the cumulative distribution function of a random critical bid b hat that we're offering this agent. Okay? In other words, let's think back to the first price auction and remember what was happening in that auction. Well, a bidder was bidding, and whether they win or not depends on the bids of the others, right? And in fact, it depends on the highest bid of the others, right? If the bidder bids more than the other bidders, then they win. If they bid less, they lose. And so what we care about is the distribution of the highest of the other bids. And in fact, that distribution is exactly this x tilde. Okay, so we can view x tilde as the CDF of a random critical bid for this agent. Okay, and viewing x tilde as a CDF of a random critical bid, we could calculate the expected value of that critical bid. For the first price auction, this would be the expected value of the highest other bid. Okay, so we'll call this expected critical bid b hat. Capital B hat is the expectation over little b hat drawn from x tilde. That's the CDF of the b hat distribution. Okay, and using a definition of expectation for non-negative random variables, you can calculate the expectation of a non-negative random variable as the integral of 1 minus the CDF, which in our picture has the following geometry. It's the area above the allocation rule. Great. So what we're going to do is we're going to summarize the competition that the bidder faces by this capital B hat, this expected critical bid. Okay? And we're going to say that either the agent's utility is big, meaning this blue rectangle is big, or the reason why it's not is because the orange area, this expected critical bid, is big. Okay? And when we say big, we mean sort of relative to the agent's value. Okay, so I want to depict the agent's value on this curve now. The agent's value is simply the area of this rectangle. Okay, with width equal to the value and height equal to 1. Okay, so what we're saying is geometrically is the blue area plus the orange area cover a large fraction of this rectangle we get with area V. Cool. The lemma that we're going to be able to show is the following, that the utility, the blue area, plus the expected critical bid, the orange area, is at least an E minus 1 over E fraction of the value of the agent. Okay, we'll look at this analysis on the next slide. Okay, that's the geometry of best response. Cool. The next thing I wanted to talk about is a quantity I call the conversion ratio. This is the extent to which a mechanism converts competition into revenue. Okay, and again, competition is this B hat, okay, the expected critical bid the agent faces. Okay, so this conversion ratio is going to quantify the extent to which, which we'll call mu. It's going to quantify the extent to which, if agents face high competition, it leads to high revenue. Okay, and we'll define it as follows. Okay, so the conversion ratio mu is going to be the max over all bids you could potentially put into the auction of the optimal way to allocate, imagining those bids or values. So suppose you wanted to maximize the 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 sum of values of the bidders. So then that's what op would do. But what if instead of values we put in these expected critical bids for the bidders? Okay, so mu is maximizes overall bids, the ratio of these the optimal sort of welfare of critical bids to the revenue that we got with those bids. Great. Okay, and so here's the theorem I want to prove. If we have a auction that has conversion ratio mu, then its Bayes-Nash welfare is mu times e over e minus 1 approximation. Cool. So in the next slide, we'll be, or in a few slides, we'll show that there are some auctions that we like that have mu equal 1. Okay, so mu equal 1 implies an e over e minus 1 approximation. Great. Let's walk through the proof of this theorem. Okay, so we'll start with our lemma. Just rewriting it here, but for agent I. Cool. I'm now going to take the welfare optimal allocation, the welfare optimal ex post allocation, x star, which maps valuation profiles to the set of people who win to maximize welfare. Okay, and I'm going to take my previous equation and imagine I multiply x star I through all sides of the equation. Okay, well, it's a probability, so x star I is a number less than 1. Okay, so if I take the first term and I increase it to 1, I only make that inequality better. Okay, so this second line is the same as the first line. When I multiply x star I, which is the number between 0 and 1, throughout both sides of the equation, and then I take the first term and I increase it to 1. Great. Now I'm going to sum over all agents I and apply the conversion ratio. Okay, so in particular, what I want you to look at is summing over all agents I. So I sum over all the utilities, I get the total utility. Okay, I sum over all agents this vi times xi star of v, which is value times the optimal allocation given the valuation profile. And I get the optimal welfare times e minus 1 over e. Okay, good. So the remaining term in the middle, I have this sum of bi hat times xi. Okay, so that is a feasible allocation, okay, because xi star is a feasible allocation, summed over all agents of the expected critical bids. Okay, but we know from the conversion ratio that the optimal way to feasibly sum expected critical bids, the ratio of that to the revenue for these bids is at most mu. Okay, so factoring the revenue onto this side of the equation, we know that mu times the revenue is at least the max over, it's at most the optimal welfare of the critical bids. Okay, so so this quantity is upper bounded by mu times revenue. Cool. Now what I'm going to do is just take expectations. Okay, if I take expectations, and I'm going to use the fact that mu is at least 1 to factor a mu out. And so I get mu times utility plus mu times revenue, but mu's and utility and revenue is equal to welfare. So mu times welfare is at least e over 1 minus e times opt. Cool. Okay, I now want to prove the lemma. So the lemma that we were using was that either the utility or the competition is high. In particular, the sum of the utility and the competition is at least a e over e minus 1 fraction of the agent's value. So I'm actually going to prove a simpler result, and you can look in either the original papers or my textbook manuscript for the proof of the better bound. Okay, we're going to prove that either the utility or the competition is at least half of the value. Cool. So here's the picture we had before. And again, what we want to show is that the blue area plus the orange area covers a large fraction of the rectangle with area equal to the value. Good. Well, we're going to look at the following bounds. Okay, so the blue area is the biggest rectangle underneath this curve. So it's certainly bigger than this rectangle I've drawn here. Okay, and the allocation rule x of b, the bit allocation rule, is monotonic. Okay, so the orange area is certainly bigger than the shaded area in the upper left corner. Cool. And it's easy to observe that because I've put the value exactly, the bit of exactly v over 2 in here, that these two shaded areas are exactly half of v. Great. And as I said, a more careful analysis will give an e or e minus 1. We'll leave that to later time. Okay, so I now want to show you that some auctions have a good conversion ratio. Remember that a conversion ratio, the intuition is that high competition, an auction with a good conversion ratio is one where high competition leads to high revenue. Okay, and again, we've defined this conversion ratio to be the maximum over bids of the optimal welfare we could get if the values were equal to these expected critical bids over the revenue. Okay, so the analysis I want to give you is to show that the conversion ratio of the first price auction is mu equal to 1. Okay, this is going to be a fairly straightforward analysis. Let's fix any bids B. Okay, this is a deterministic set of bids, and so the outcomes are not randomized. So the expected critical bid faced by bidder I is exactly equal to the highest of the other bids, which is a deterministic bid, which I'll call little bi hat. Okay, so there's no randomization here, so it's all deterministic, and this is the critical bid that's faced by bidder I. It's the highest of the other bids. Great. Well, what is the revenue of the first price auction? Well, the highest bidder wins and pays their bid. So the revenue is the maximum over I of BI, the highest bid. Okay, but look, rewriting it just a little bit, the max over BI is equal to the max over I of the max over J not equal to I of BI. Okay, in particular, one of these maxes is going to have the highest bid in it, and so the max over that is going to have the highest bid in it. Cool. But this is just the max over I of BI hat. Okay, and this is the optimal welfare we could get if we were maximizing over the expected critical bids. Okay, and so that is the definition of just opt of B hat. Okay, so this revenue is equal to the optimal welfare from the critical bids, and so this ratio is equal to 1. Great. I want to talk about some properties of conversion ratio because what we've done right now is we've shown that up to a factor of e over e minus 1, the welfare in equilibrium is essentially equal to the conversion ratio. And so if you want to know if an auction has good welfare, all you have to do is determine if it has a good conversion ratio or not. Okay, and so there are a number of properties of conversion ratio that make it especially convenient for analyzing. I first want to note it's not an equilibrium property. Okay, here was our analysis for the first price auction. We didn't have to do any complicated thinking about strategies or equilibrium or anything. We just looked at bids and we asked, what's the, how bad could it be, this ratio of revenue to critical bids for those bids. Okay, so it's typically fairly straightforward analyses lead to bounded conversion ratio. There's some environments where it's tight, where the conversion ratio sort of exactly corresponds to the welfare that you're going to get in equilibrium. It's closed under simultaneous composition, meaning if I have some auctions that each have some conversion ratio, and I want to run all these auctions at once, then the conversion ratio of the composite mechanism is equal to the worst conversion ratio of any of the individual mechanisms. Okay, it's also closed under randomization, meaning if I'm looking at randomized mechanisms, mechanisms that are distributions, say, over deterministic mechanisms, or if I'm looking at random bids and not deterministic bids, then it suffices to analyze the conversion ratio of each deterministic mechanism in the support of the distribution, and the conversion ratio of the randomized mechanism is no worse. Okay, so that makes analyzing things like the position octa we talked about previously very easy. Great. So we just talked a lot about how to show that equilibria are good. I now want to talk about situations where equilibria can be bad. So in particular, I want to look at the winner pays bid, highest bid wins mechanism and talk about how it may have bad equilibria. Okay, and the example I want to look at is the single-minded combinatorial auction. In fact, this example is a generalization of the example we gave before with the exclusive ad space or the 3 shared ads. This is just a generalization of that example. Okay, so I want to give you a scenario of a single-minded combinatorial auction where we'll show that the conversion ratio is bad and also the equilibria is bad. Okay, so in this example, we'll have M items for sale. We'll have M plus 2 agents. Agent I is going to value getting item I and have value 1 for item I. Agent H for H in M plus 1 or M plus 2, so they'll have 2 agents who value the grand bundle of items, meaning they want to buy all of the items. Okay, and they have these 2 agents have value 1 for this grand bundle. Okay, so think about connecting this back to that example of exclusive ad space or shared ad space. So again, I have these agents who want to share the space, and each of them is happy for their own third of the space. But I have these other 2 agents who want the whole thing. Okay, they want all of the space, the ad space. Okay, so here's a Nash equilibrium. The Nash equilibrium is, we'll have these 2 agents, H is M plus 1 or M plus 2, bidding 1. Okay, look, one of them will win, one of them will lose. Maybe we break ties randomly, doesn't matter. All the other agents are going to bid 0, and all will lose. And I want to note that imagine a deviation that any of these bidders could make. If anyone bids to deviate anything less than or equal to 1, everyone else still has 0 utility. Okay, so everyone's utility is 0 right now, and anyone, for any bid they put in between 0 and 1 is also going to have 0 utility. Okay, these little agents I are all going to lose. and have 0 utility, or if they bid 1, they might win, but their value is 1 and they bid 1, and it's a winner pays bid mechanism, their utility is 0. Okay, likewise for the high valued agents. Okay, so the Nash welfare here is 1. What's the optimal welfare though? Well, look, all these little valued agents all had value 1. There were m of them, and we could have given them each their own object. We could have given object I to agent I, and the, agent I would have gotten value 1 for that, but we chose not to. Okay, so the optimal welfare that we wish we'd gotten is m. Great. I claim the conversion ratio of this auction is mu equal m. Let's look at it. Let's look at the critical bids. Okay, so what do all the little agents I have to bid in order to win? Well, if any of them bid above 1, well, suddenly they're the winner. And so their critical bids are all 1. Okay, what are the critical bids of the bidders with value h? Well, likewise, because there are 2 of them, they have to bid above 1 to win. Okay, so all the critical bids are 1. Okay, so what is the optimal thing, the optimal allocation if we're trying to maximize the sum of these expected critical bids? Well, that optimal is going to be equal to m. Of course, the revenue of this equilibrium is 1. And so the ratio of the optimal to the revenue, the optimal surplus of these expected critical bids to the revenue is m. And that's the definition of the conversion ratio. And so we see the conversion ratio is mu equal m. Cool. So we just saw that optimally allocating in the single-minded combinatorial auction leads to a really bad m conversion ratio. It turns out the greedy single-minded combinatorial auction can do much better. So what is the greedy greedy winner pays bid mechanism? The bidders bid. We're going to allocate greedily by some priority function. What does that mean? We're going to sort the agents by their priority, and then we're going to try to allocate to the agent with the highest priority. If we can, great. Otherwise, we discard, and then we repeat going down the list of priorities. Okay, so we're trying to allocate to each agent in order of priority while we still can. Okay, and in the end of the day, the winners will pay their bids. Cool. So you can prove the following theorem, which I'm not going to do here, but the conversion ratio mu of a greedy winner pays bid mechanism is equal to the approximation ratio of the greedy algorithm with the same priorities. Okay, so if I have the greedy algorithm that gets a good approximation, well, the conversion ratio of the winner pays bid greedy mechanism is going to have the same. It's going to have the same conversion ratio. In other words, mu is equal to beta, the approximation ratio. Okay, and Lehman, O'Callaghan, and Shoham showed that greedy by bid divided by square root the size of the bundle that a bidder is demanding, that algorithm is a beta equal to square root m approximation. Okay, so combining these two theorems, we see that the Bayes-Nash welfare of the greedy winner pays bid mechanism is square root m times e over e minus 1. Okay, in fact, and you might ask now, okay, well, we saw that the highest bid wins, winner pays bid mechanism, has a conversion ratio of m for the single-minded combinatorial auction. This greedy algorithm has a conversion ratio of square root m. Well, maybe there's some better auction that has a better conversion ratio. But in fact, Dudding and Kesselheim showed that a conversion ratio of mu for any winner pays bid single-minded combinatorial auction is no better than square root of m. Okay, so in fact, this greedy algorithm gets the best conversion ratio, uh, uh, and therefore is in a sense, via these techniques, the auction that has the best uh, equilibrium performance in worst case. Cool. So this was a bit of a downer. In fact, we looked at these settings, which seem important, these combinatorial auctions. And in fact, combinatorial auctions, this model of single-minded combinatorial auctions is motivated by the very practical combinatorial auctions that have been very useful for selling things like the FCC spectrum that cell phone companies use. So this has been a bit of a downer. We'd like to design mechanisms that have good equilibrium, and yet, we have a lot of evidence that shows that, getting better than a square root m approximation in worst case in equilibrium is going to be is not something we should expect. Okay, so the question I want to leave you with and close this section out is how can we design near optimal non-truthful mechanisms?